Welcome back. Or welcome, if you're starting in the middle of this for some reason. Cool. Like people that try new things for no clear reason whatsoever. The following is the reading for lectures 10 and 11, apparently, in MIT OpenCourseware's 6.100L, Introduction to Computer Science and Programming Using Python. Except the readings for lectures 10 and 11 both include 5.3, which was the last section included in the reading for lecture 9. So I'm not reading that again, just go back to that video and watch it there. You might be wondering why I'm wearing a sheet. Higher order operations on lists. In section 4.4, we introduced the notion of higher order programming. That's where a function takes in another function as an argument. It can be particularly convenient with lists, as shown in figure 5-5. Check it out. It's explained well enough in this next paragraph that I'm just going to jump to that. The function apply to each is called higher order because it has an argument that is itself a function. The first time it is called, it mutates L. Where am I? Apply to each. By applying the unary built-in function abs to each element. The second time it is called, it applies a type conversion to each element. Integer. And the third time it is called, it replaces each element by the result of applying a function defined using lambda. It's an anonymous little rogue function here that's defined just in this one little line. It takes in x, and it returns x to the second power. And all this together, it prints this. The original list, the list mutated by the absolute function, the list turned only into integers, and the list, each element of which has been squared. Python has a built-in higher order function, map, that is similar to but more general than the apply to each function defined in figure 5-5. In its simplest form, the first argument to map is a unary function. That is, a function that has only one parameter, unary, as opposed to binary, or ternary, or quaternary, or you know what I'm saying. And the second argument is any ordered collection of values suitable as arguments to the first argument. It is frequently used in lieu of a list comprehension. For example, like here, which is equivalent to a list comprehension that does the same thing. Now here we got a function as the first argument. Here's an ordered collection of values suitable as arguments to the first argument. Those two are passed in to this now higher order function map, which will map the values of this to this, right? And it will turn the output of that into a list. And that's equivalent to a list comprehension, which, using square brackets and some logic, will generate a list for you, which would accomplish exactly the same thing here. The map function is often used with a for loop. When used in a for loop, the map behaves like the range function, in that it returns one value for each iteration of the loop. These values are generated by applying the first argument to each element of the second argument. For example, the code for I in map of lambda function, which takes in x and returns x squared, comma space, a list containing 3 integers, 2, 6, and 4. For I in the mapping of this function to this list, print I, meaning it will iterate over each element in this list, apply this first argument, the lambda function, to each element one by one, and output that one by one, each on new lines. So it will produce a list of 3 squares on 3 separate lines. 4, 36, 16. More generally, the first argument to map can be a function of n arguments, in which case it must be followed by n subsequent ordered collections, each of the same length. For example, the code. We got one list. We got a second list. And we got for I in the mapping of the min function to L1 and L2, 2 ordered collections, each of the same length. This will print I. Now this will print 1, 28, and 9. And that it will iterate through and compare them, map the min function to them. So it's, what's the min between 1 and 2? 1. What's the minimum between 28 and 57? 28. What's the minimum between 36 and 9? 36. Ooh, whoops. No, it's 9. Finger exercise. Implement a function satisfying the following specification. Hint. It will be convenient to use lambda in the body of the implementation. This function will be called f. Horrifically. Has 2 parameters. List 1 and list 2. L1, L2. Lists of same length of numbers. Returns the sum of raising each element in L1 to the power of the corresponding element, the element at the same index, in L2. For example, passing in a list which contains 1 and 2, and a list containing 2 and 3, into our horrifically named function, will return 9. Because 1 squared and 2 cubed added together presumably equals 9. Not even gonna do that much arithmetic in my head right now. How far does this go? 5.3 to 5.5. Almost there. Strings, tuples, ranges, and lists. We have looked at 4 iterable sequence types: str, tuple, range, and list. They are similar in that objects of these types can be operated upon as described in Figure 5-6. Some of their other similarities and differences are summarized in Figure 5-7. Let's take a look at Figure 5-6, which outlines common operations on sequence types. Seek, at index I, returns the ith element in the seek. Len, seek, returns the length of the seek. Second plus sec2 returns the concatenation of the 2 sequences. It's not available for ranges. In times sequence returns a sequence that repeats sequence in times. It's also not available for ranges. Seek start colon end. Now this will return a slice of the sequence, and you're not actually going to put the word start or end in here. You understand that, right? These are the starting number and the ending number that you'll be putting in place of these little placeholder words. E in sec is true if E is contained in the sequence, and false otherwise. Just does it exist in the sequence? E not in sequence checks for the opposite. For E in sequence iterates over the elements of the sequence. These are all common. Dime a dozen. Comparison of sequence types. Types true. Elements are characters. Okay, here's some examples. Mutable, no. Tuple. Remember the hug? They can have any type, including tuples inside them. Here's some examples. Just remember, when you get a singleton, it has to be followed by a comma nonetheless, despite having no compatriots from which to separate using this comma. Type range. Type of elements, integers. Come on, we know this one. And no, it's not mutable. List, also any type. Here's some examples. This is the only one, can be mutated. You can really go nuts on a list. Python programmers tend to use lists far more often than tuples. Since lists are mutable, they can be constructed incrementally during a computation. For example, the following code incrementally builds a list containing all of the even numbers in another list. First, it is defined. It's named even elements, empty list. And for E in L, which we're assuming is a predefined list earlier in the code for this example, if E modulo 2 is equal to 0, then append, using the .append method, to the end of our empty list, what we find there at E. If it's even, add it to our list even elements. Once this is done and iterated through all of the elements in list L, our formerly empty list will be full of nothing but even numbers. Cool. And divisible by 2. Since strings can contain only characters, they are considerably less versatile than tuples or lists. On the other hand, when you are working with a string of characters, there are many useful built-in methods. Figure 5-8 contains short descriptions of a few of them. Keep in mind that since strings are immutable, these all return values and have no side effect. S.count, which takes an S1, counts how many times the string S1 occurs in S. The .find returns the index of the first occurrence of the substring S1 in S, and -1 if S1 is not in S. The .rfind method, same as find, but starts from the end of S. The R stands for reverse. .index method, same as find, but raises an exception. Chapter 7, if S1 is not in S. The .rindex, can we guess? Same as index, but it starts from the end. .lower converts all uppercase letters in S to lowercase. .replace, which takes in 2 arguments, replaces all occurrences of the string old in S with the string new. It replaces, okay. .rstrip removes trailing white space from S. So any extra spaces at the end of a string. And .split splits S using D as a delimiter. That is a chosen character of your choice that will be the standard thing that used to separate elements. Often a comma, for example. Returns a list of substrings of S. For example, the value of David Guttag plays basketball .split with a string containing only one white space is David, comma space Guttag, comma space plays, comma space basketball. If D is omitted, the substrings are separated by arbitrary strings of white space characters. One of the more useful built-in methods, split, which takes 2 strings as arguments. The second argument specifies a separator that is used to split the first argument into a sequence of substrings. For example, print these strings with the .split method applied with white space or with a hyphen Or with a hyphen again? What? The second argument is optional. If that argument is omitted, the first string is split using arbitrary strings of whitespace characters. Space tab, new line, return, and form feed. Still not clear why the output on these two is actually different, because this does look identical. And it's hard to trust this book because it's full of typos. But no matter, you've done the reading for lectures 10 and 11 now.